All right, so for this week's One World Mind seminar, we're very happy to have Professor Andrea Bertozzi with us from UCLA to speak again. She's the distinguished professor of mathematics and mechanical and aerospace engineering, as well as the Betsy Wood Knapp Chair of Innovation and Creativity and the Director of Applied Mathematics at UCLA. And she also gave the very first seminar back in April of 2020. So we're delighted to have her back for a pandemic update as we continue to enjoy something that was sort of very uncommon, or significantly less common a year and a half ago, the mighty Zoom seminar. So I'll turn things over to her to let her talk about modeling pandemic related data and so forth.
Yeah, thanks very much. It's a pleasure to be here. And thanks for your interest in our work on COVID-19 modeling. This is one, I don't give this talk as much as I give some of the other talks. So I'm really pleased to have people interested in this topic. So without further ado, let me just go. So I have to say that I got interested in COVID just because, I'm interested in the world, right? And I think it was January of 2020, roughly, when I heard about this virus getting out of China. And, I'm old enough to remember quite well the SARS outbreak in 2003. In fact, that was the spring I was planning my move from Duke to UCLA. And, you start sort of thinking, uh-oh, so this is like SARS again. And then realizing that, based on early data, that this was not going to be like the SARS outbreak. The SARS outbreak was a more deadly disease, but it was very much contained. There were some outbreaks in various places, like Toronto, I remember, was one of them. I was thinking about going there, and I decided not to go there. But not just because of the outbreak. There were some other just personal issues with my move. And, I was watching this thing unfold early on, and, I wasn't at the time an epidemiologist. I'm still not, but I've learned a lot more about epidemic modeling since then. But, as somebody who's worked for decades in nonlinear dynamics, it was pretty easy to kind of dust off the simple epidemic models and just start running some numbers, right? And, and so when the Imperial College report came out on March 16, this was certainly not a surprise to me, and was not a surprise to a number of my colleagues and collaborators. And this report had a profound impact. So this is, a good example of how mathematical modeling can have an immediate impact on policy, and an impact that also can be controversial. So I want to talk about that too. So what happened was, on March 16, Imperial College released, they have a very famous group in epidemic modeling. They've run influenza simulations for a long time. And they took their influenza model and basically plugged in the parameters that they knew of for COVID, and predicted that without some kind of shutdown, that, if we just kept on with business as normal, that we would see the following kind of outbreak in the UK, an earlier peak kind of in late May to June, with about, deaths, with like 500,000 deaths, and that the US, would see over 2 million deaths happening like by early summer. And that's, of course, a big number. And you all know, so it's now controversial. Why controversial? Well, have we seen 2 million deaths, over 2 million deaths in the US? Absolutely not. But we have seen about 600,000, which is still a number that's pretty big. And so one of the challenges with mathematical modeling of epidemics is to try to understand the differences between what we're showing here. This is a good example of a counterfactual model. So it like never happened. And I don't think there was any intention for it to happen. And the point was to basically be a fire alarm, right? This is a counterfactual model. Another kind of model that you can look at that can use very similar kinds of dynamics, right, would be a forecasting model. And so I'm going to talk about some of those, the differences between counterfactual models and forecasting models. But sure enough, like when you produce a counterfactual model like this, as you can imagine, you know, you get a lot of people who aren't science. I mean, it's out there for like lay people just to read in the news, right? People who have no connection to science whatsoever. And of course, those people are going to get upset when they see that they were, you know, supposedly predicting 2 million deaths in the United States. And of course, we haven't seen anything like that. So, you know, that's a good story for someone who wants to shoot down the scientists and say, oh, they don't know what they're talking about. So, you know, I think for those of us who are going to try to do this kind of work, part of the message to the public needs to be really clear, right? This wasn't this paper wasn't telling people that, you know, no matter what, this is going to happen. It was more along the lines of, you know, if you don't do something, we can see this kind of behavior, right? So that's an important distinction. Of course, some of the details often get lost when you get to media reports from different angles. But anyway, this is something as a modeler that is like really, really basic, and I think it's important for, you know, especially for younger mathematicians to understand that if you're going to be doing modeling of very important things like this, that, you know, there are going to be issues that go way beyond like the actual math. And I also want to say that before this report came out, I was taking numbers and just running them on a basic SIR on like an Excel spreadsheet, you know, because you know, you sort of like seeing the future train wreck, right? And yeah, like this is a more sophisticated model, but a standard SIR model will produce the similar kinds of numbers to what you see here. So this was not a surprise for you know, sort of the armchair epidemiologists. This report was not at all a surprise. Okay, one of the interesting things about COVID, and we're seeing this now, right, over a year later, is the difference in the outcomes as a function of the age of the population, and also, of course, various comorbidities, right? So, in particular, what we're seeing is that people who are in the elderly population have a pretty high, you know, fraction who require hospitalization, and the fatality numbers are also much higher than the young. I mean, it's dramatically different, right? If you look at, for, you know, college students today who are like in this bucket here, you know, you have a very tiny chance of death, whereas if you're over 80 years old, you're looking at, and this was early data, by the way, but these numbers haven't changed too much. You're looking at a much higher chance of death, right? So that's another aspect of the disease that had to be understood. And you know, my sort of armchair and Facebook discussions with science friends led to a study that several of us put together on how does one take early time data from a pandemic, which we hadn't seen in 100 years. So it was a very exciting problem to work on. Data, you know, that's sort of the first of its kind in 100 years, and you're getting it in real time. And what do you do with that, right? And so, you know, the standard thing in epidemiology is, you know, I would say that for every epidemiology group or expert, they have their own model, right? So there's a lot of models floating around there. And you might, for those of you watching the news back in like March and April of 2020, might remember that there was the quote unquote Washington model that the White House was using, and they were putting charts up on their national briefings, but then there were lots of other models floating around, and they were all doing different things. And how do you know how to pick one? So that's one of the things I want to talk about today. And this is really challenging when you're working with early time data. So there are kind of two things you can do. You can do the backwards look and say, okay, after you've had a pandemic, can you use models to understand the data? So we'll look at an example of that. But I also want to talk about early time data. And very few people, if any, try to compare models, you know, other than just running them and looking at to see how well they did. So I want to talk a little bit about a very standard method for comparing models with sparse amounts of data, and that's the Akaike information criteria, which is well known in statistics. Okay, so so one of the things that you can do with early time pandemic data is you can look at trying to measure reproductive numbers, and I don't think that needs any explanation today, because I think even like 3-year-olds know what reproductive numbers are. I mean, I'm exaggerating, but you get the idea, right? This is, it's basically exponential growth at early times. You want to understand how to estimate, your infection rate by that. And so my colleague, Elisa Franco, she's a professor at UCLA mechanical engineering. She's from Italy. And of course, being from Italy, and Italy just got clobbered early on in the pandemic. She was busy calculating a lot of growth rates for different European countries and kind of comparing them to what was happening in the US. And of course, we lagged behind the UK and Europe, right, in terms of the initial infections, just because of travel patterns prior to the travel patterns during the very, very early days of the pandemic. So one of the things that you find with the initial exponential growth is there's actually kind of two numbers, right? So there's and I'll get to the epidemic, I'll get to the compartmental models in a second. But there is a transmission rate of infection, but there's also a recovery rate gamma. And those are two different numbers. And it takes some time for people to recover. It's usually, a couple of weeks until you're really seeing that effect. So what happens is that at very, very early times, your exponential growth is basically just seeing the parameter beta. But once you start getting some recovered population, then the cumulative infection count is going to reflect this difference between beta and gamma, right? So that's one thing that if you're actually just looking at raw data, you're going to want to try to find both beta and the beta minus gamma and somehow embedded in the data. So that's one of the things that we noted for early times. That brings us to the standard, the simplest of the compartmental models that's relevant to COVID-19, which is the SIR model, susceptible, infectious, recovered. And so this one, we did some kind of work, kind of pulling apart in a way that, it's not too hard to do it, but it hadn't been studied in this way in the prior literature. And so this comes from, being non-epidemiologists who are trained, we are trained more in, I would say, physics modeling, where you look for things like dimensionless parameters, and then try to look at how to rescale different scenarios to the same kind of dimensionless models. So that's pretty straightforward to do. And if you're ever teaching a class in, say, ordinary differential equations or differential equations and modeling, and you want to teach the students about dimensionless parameters, this is actually an interesting, fairly easy model. It's an ODE. There's no spatial derivatives or anything like that. It's just time. So it's not that hard to do. So here's what you get. So if you take your standard SIR model, so let's just describe it. You've got compartments. Each compartment has, your entire population is going to live in one of these three compartments, and they will move over time, right? So at the beginning of a new pandemic, I see there's a chat. I don't know what's going on in the chat, but if you guys have something you want to interrupt, you can just interrupt.
That was me telling people they could ask Q&A tool. So.
Yeah. Okay. So I don't know. I'm assuming that there's fairly good knowledge of SIR at this point. So but just to remind you all, that in a new virus, like where nobody has it at all, then basically almost the entire population minus the initial seed infections, right, are susceptible. And then there's some rate at which you become infectious, and that rate is nonlinear, right? And this is a simple physical phenomenon that in order to become infectious, you have to come into contact with somebody who has a disease. If you have nobody who has a disease, nobody will there will be no outbreak, right? So if we go back to, I don't know, to 2015, right? COVID-19 wasn't here because nobody had it. Right. So at least we believe that. Right. So, initially, you're not going to see a lot of, you can't like take like half the population, have them suddenly get infectious. if you have nobody or very few people who have it, right? That's why you have this sort of gradual but exponentially increasing rate. So it's this nonlinear product. It's the susceptibles times the infectious, right? And that represents a simple contact, one-to-one contact, right? And then there's a transmission rate beta. And beta is a function of how infectious is the virus itself. So beta is all about biochemistry, right? And S and I are all about the number counts of people who have the disease. And then notice that you have a linear model, almost that's basically in the same form as like linear control, if you will, that takes the infectious population and then removes them from that category with some rate constant gamma. And so the reason why this is linear is because to recover from the disease, you don't need to come into contact with anybody. You could be suddenly on a mountain by yourself and you will recover at some rate, or you could be in the general population and you will still recover at that same rate. So that gives you a linear behavior, and then you can run simulations of this with using a stochastic model that's very discrete, that looks at individuals, or you can look at the mean field limit, which is this ODE down here. So this is our mean field limit, and we get a coupled set of ordinary differential equations. And this is the dimensional form, right? So this is the total number of people, N, I is the total number infected, S is the total number of susceptible, T is time, beta and gamma are the two constants, the two rate constants for transmission and recovery. And then the first thing you notice is that you can get rid of these transmission and recovery rates that are dimensional by dividing by the recovery rate gamma on all of the equations. And then suddenly your rate constants are just either one or this dimensionless number, which is the famous R naught, beta over gamma. That's the reproduction number. The equations still aren't dimensionless, but it's very trivial to make them so by just taking each of these populations and dividing by the total number in the entire world, so that you get percentages, fractions of the population. So we call those little s, little I, and little r. And that gives you a completely dimensionless model. And so then you can kind of look at that and have fun with that. Okay, and by the way, you get graphs that look like this. You start with your susceptible population is almost the entire group. That will decay over time. There's the infectious group, and then there's the recovery group here, as we can see. And one of the takeaways here, for those of you who are not experts in epidemiology, is no matter what R naught is and what conditions you start with, you will never end up at time, as time goes to infinity, you're never going to have your population completely recovered. There will still be susceptibles in the population. So the long time limit is not S going to zero. It looks like it's going to zero here, but it's not. It's always going to some number, and how far down it goes, right? How much of your total population is infected depends directly on R naught. That is the key. And so that's important when we're thinking about vaccines today, right? The fraction of the population that is vaccinated and who may have immunity from having had the virus. That number is important because it tells us, when you compare that with R naught, you can get an idea of, sort of what the end state could be and where you are. And if you're not at that end state, if you still have a lot more susceptibles than the end state that's given to you by R naught, and there's a bunch of different end states, we'll get to that, then you should expect outbreaks to continue. And that's exactly what we're seeing today, especially with the Delta variant that has very likely a higher R naught than the original virus that was, that made its way across the world over a year ago. Okay, so a couple other things about SIR is that you have basically conservation of the total population, unless of course you include death, and you can include death in the model. It's not too hard. For a simple SIR, sort of from a modeling perspective, you can just say that some of the people who died are actually taken up by the R population. That's kind of a morbid way to look at it, but it doesn't really change the model too much. Where it becomes relevant is if you want to look at more complicated models where people can get reinfected, right? If you're dead, you're not going to get reinfected again, right? So, but including the death rate is very easy to do, right, in a standard SIR model. Okay, another couple of things that we have that we can compute, like just on pen and paper without having to do simulations, is the long time behavior, as I mentioned. So, you can get an exact solution to these equations by taking the first equation, dividing the first equation by the last equation. Gives you some sort of nice formulas, right, that you can look at. So here's a formula for S in terms of R, and in particular, you can get exact expressions for the long time limit of little s, right, which S infinity would be as time goes to infinity, what your fraction of the population is susceptible, and how many are recovered. And you can see that there's an explicit formula that depends on a special function called the Lambert W function and the initial conditions here. So, so that's nice. So what this shows is that at the end of the epidemic, unless S naught equals 0, not all individual populations are recovered. This is what I said earlier. This means that the end of an epidemic is caused by the decline in the number of the infected individuals rather than an absolute lack of susceptible subjects. And this is an example of what we call herd immunity, right? So you may have heard the words herd immunity with respect to vaccines. So the question is, how much of the population do I need to vaccinate to get the epidemic to stop so that there's no more outbreaks? So the point isn't to vaccinate everybody so that everybody is immune. The point is to vaccinate sufficient number so that you're not going to get these sort of somewhat uncontrolled outbreaks. Okay. And yet, you can have fun with this. You can look at phase plots. This is a phase portrait of infected versus susceptible. And one of the things you get from the phase portrait is that that you can see where your peak in the infected population is going to occur, right, at 1/R0. That's when the percent susceptible is 1/R0. Right, and so, right, so let's see, what else do I want to say about this? Yeah, okay, I think I have a lot to talk about, so I think I'm going to skip this slide for the moment. Yeah, okay, so this is an important slide. So this is from an old paper that I really like. I'm going to talk a little bit about this paper. This is Bootsma and Ferguson, PNAS 2007, and it's looking at, well, so part of the paper looks at the data from the 1918 pandemic. Very interesting study, but this chart is not from that. This is just a model. This chart is basically trying to explain, and I really like it, the issue of herd immunity and how you can get different outcomes based on a control of the pandemic. So, so this is why doing some kind of distancing can actually save lives, even in the absence of vaccines, right? I mean, it's not gonna save as many. It's going to save far fewer lives than vaccines would save, but still you get some benefit in terms of saving lives. So let's look at this. So what we're looking at here on the left is the proportion of the population that will at some point become infected based on two scenarios. One is an uncontrolled outbreak, which is the blue curve here. And the other is the minimum amount of control that you need to, how can I say? Yeah, the minimum, what's the right word here? It's based on the amount of control that you need to exactly at your end state reach herd immunity. right? So basically you could have, so now this is what, so let's look at an example. Let's take R naught equals 2. And if you take R naught equals 2, which is the example we're going to look at on the right, what you see is that, and this, let's see, so what you see is that the uncontrolled pandemic, right, which is kind of like where COVID-19 was in terms of the original virus, not the variants, right? So this was saying that if you let the disease go uncontrolled through the population, you're going to expect like 80% of your population to eventually get infected. But if you let the outbreak happen with some controls, so you slow the transmission of the disease using distancing measures, masks, whatever, what happens is that, so in this particular case, we're reducing it to the point where only 50% get infected, and that actually is enough to reach herd immunity with this particular R naught. So now what we see on the right is the actual outbreak as a function of weeks. So this is the infection incidence versus time. And we see without controls, of course, you get this big outbreak. The optimal control would be this blue one, which means you get a slightly shifted and lower infection incidence. But you can also tighten up even more. And what you see is that if you do that, which is the red line, when you loosen up the controls, you're going to have a second wave. And we have certainly seen that a number of times with COVID. Now, you may ask yourselves from a policy standpoint, was it wrong to a critic could say, oh, we shouldn't have reduced the interactions. We shouldn't have shut down so much because you get second waves and then more people get infected. So that's one way to look at it. Another way to look at it, though, would be that if you can do the red curve, which is probably going to save even more lives on the short term, while simultaneously developing vaccines, and now, of course, you're not going to have new vaccines ready in 12 weeks. We know that, right? We know that even with Operation Warp Speed, it took like a year or almost a year to start getting them into arms. But nevertheless, like in a fictional situation like this, if somehow vaccines showed up at week 12 and they were effective, you might kill the second wave. So there are, from a policy standpoint, there are some advantages to shutting down further than what's needed just to reach the herd immunity. The other thing I want to mention about herd immunity is yeah, sorry, just a little, yeah. I actually, no, I think I'm gonna skip to the next slide. All right, so another thing I wanna mention about this dimensionless scaling of SIR is that it gives you some parameters that can be used to compare outbreaks in very different parts of the world. So if you happen to, and by the way, the local R naught may be different, and like just because, so it's not just at some level it is a function of the transmission rate and it is the transmission rate over the recovery rate. However, the transmission rate is dependent on your population density, right? So the transmission rate, and I'll show some slides from this later on. Early on in the pandemic, what we saw was a huge increase in cases in the New York City, New Jersey area. And that was a function of a couple of things. One was that you had travelers coming from Europe, many of whom were arriving in New York versus other locations that were helping to increase the amount of new infectious cases in those areas. But also you have, like, especially in Manhattan, you have a very high population density, right? At the same time, I was in California, I was actually in New York in early February, but I was back in California when, the shutdown happened. And same time, we didn't see nearly the same rate of initial infections here in California. And part of that was that, we're a little more spread out than Manhattan. So that was a good thing for us. But also there's the time effect. So let's try to break that down here. So in the dimensionless model, one of the cool things you see is that if you have almost no infections at early time, your dimensionless model with the same R naught, if you take different simulations with the same dimensionless R naught, they all collapse on each other, which is pretty cool. There's like a universal set of curves, which is what we're looking at here. So when I say collapse, how do we make them collapse? And the way you make them collapse is by doing a time shift on your horizontal axis, right? So here I show in this little inset that you have the time until the peak infection, which is shown on this axis. And then epsilon is the initial fraction of the infected population at time 0. And you can see that you get a series of curves with different epsilons that are virtually identical to each other, just shifted in time. Right? And so that's another cool feature of the SIR model. So it means that if you have two cities, one of whom starts the outbreak earlier than the other one, and they have effectively the same reproductive number, you know what's going to happen in the second outbreak, because it's just going to be a time shift of what happened in the first one. So that's pretty cool. All right, and I have a lot of things to cover. So I think I just covered most of this slide in what I just said. So I think I'm going to skip to early time specific cases. So we were looking at California and New York, the states of California, New York, and Indiana. And these are counterfactuals, okay? So now we're going to get into, are we doing counterfactuals, or are we trying to do forecasting or estimating parameters or choosing models? So this is an example where we've chosen to use the SIR model, and we've chosen parameters from the model that we fit with early time data. And in a minute, I'll tell you why we chose this particular model. What we're looking at here is the impact of short-term social distancing. And sure enough, that idea of the time shift comes out here. We were looking at an early outbreak in California going uncontrolled, and you can see something like this versus you might remember back in March of 2020, we had the shutdown, and then there was some rhetoric coming out of the federal government about when we could reopen. And our president was suggesting Easter. And we thought that, like, our research team thought, well, that's not going to happen. That's just a few weeks away. So we picked another holiday. We picked, as a counterfactual, right? That means it's fake. We picked May 1st, which is Cinco de Mayo, right? We said, let's pick another holiday that's like another month or two down the road. And we said, okay, what happens if you open on Cinco de Mayo? And what you see is that instead of having this initial outbreak like this, you get an outbreak that's just shifted in time, right? It's the same outbreak, it's just shifted in time. So this was a hard message, by the way. This message was trying to be, relayed to the public in various sort of soft ways early on, but it was a hard message for people to swallow, because they would be like, wait, you want us to like not go out and not do anything, and then if we open up 3 weeks later, you're just going to have the same disaster scenario just pushed back in time? And the answer is yes, right? So so our research team was looking at this and kind of realizing that we were all in for a long haul, right? That the COVID epidemic was not going to be for 3 weeks. It was going to be for a year or two, right? Which is where we are today. New York City, as I mentioned, got kind of further up that curve early on. And they also shut down a few days after California. I remember watching the news, and by the way, California, we went from like fully open to like nothing, right? It's like Tuesday, we started talking, at UCLA informally about when are they going to put us online. Thursday morning, they're like, you are online now. It was just like boom, and like the state is shut down now. Like, we're done. You're not, and all the rules showed up instantaneously. At the same time, I'm watching the TV, and the governor of New York is coming on saying, well, we're going to give people time to prepare. So he gave them an extra weekend, and we were all saying not a good idea, but anyway, that's what happened. And you can see that without shutting down at all, New York would have had a big spike quite early on compared to California. With the shutdown, we were predicting that it would be much, much less, but still you would get, like, this is with the shutdown, and you get a peak here, whereas California, we weren't going to see that at all. And then we said for fun, what happens if they open up on the Cinco de Mayo? And you can see that once you're already well into the outbreak, if you suddenly open up, you get a spurt, but you never go back to this big tall peak because you've already got a bunch of your population recovered, right? So you've got some like fractional herd immunity at that point. By the way, we looked at the serology data from New York back that was collected, I think it was back in April, from Manhattan, and it was completely consistent with our counterfactual model in terms of how many people had gotten the disease. It was on the order of 20%, from positive serology tests. That means they have antibodies, right? So that was kind of interesting. All right, I have a lot of stuff to cover. So let me just mention that there's another model called the SEIR model, which is more commonly used, especially for COVID, because what it does is it includes the exposed component. With COVID, we know that you get exposed, and then there's a lag time of on the order of 5 or 6 days, typically, from being exposed to actually becoming infectious. So that gives you that time scale right here, and it adds an additional compartment, and it adds an additional parameter. And so now you have the question of which of these models do you use, right? Do you use one with more parameters or less? There are people who would say, hey, you want to model the actual disease, you should have the appropriate number of parameters for what's happening with the disease. So that would be in favor of SEIR. And so here's an example, and this is from the 1918 pandemic. This is also from the Bootsman-Ferguson paper. What they did was they look at, so if you're looking at historical data where you have the data from the entire epidemic, the full SEIR model makes a lot of sense. So they actually included, based on historical documents, they included some interesting effects. So the transmission rate has some controls, and there's two kinds of controls here. One is this M, and the M is based on mortality, and that's basically a fear level. So people see the deaths and they say, I don't want to die, I'm going to stay home and I'm not going to catch this virus. And then this control over here with the PC, that would be the controls from the city. That's a control where the city says, we are going to force people to wear masks, we're not going to open theaters, we're not going to have parades, blah, 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 right? So those are the two kinds of effects. And you can see that M includes the death data as part of that. So what this paper did was it looked at 16 US cities for which we have death data from the 1918 pandemic. And I thought it was an interesting paper because they had to figure out they have a lot, this is a model with a lot of parameters, right? And they had to figure out whether they were going to make the parameters common for all the different cities or they were going to make them per city. And then, they had to kind of tune it, and then they had to pick which model variant they were going to publish. And I'm not going to get into all the details of how they chose this, but I want to show you that outcome because I really like this plot. So these are days from the 17th of September in 1918, 16 US cities, and the blue X's are the deaths, and the horizontal bars show you when they had controls and the duration of the controls, and the horizontal position, the length indicates the start and duration of the intervals. The vertical position indicates the estimated effectiveness of the controls. And where the top of the vertical axis is 100% effective and the bottom is 0. And then the other curves that you have here, I like these. So what they did was they fit their model to the data, and that's your red curve, right? You can see they're doing pretty good with that for all these different cities. But there's also the dark green curve. The dark green curve is your counterfactual. It's what would have happened if they didn't have the controls. And I found this really fascinating because it's a historical look at data, right? What we were doing early in the pandemic for 2020, for COVID-19, is we were trying to understand the difference between the counterfactual and what might happen with controls. We can go back and look at the historical data and see how that worked. So for example, you know, Kansas City started their control fairly early on, and you can see a marked difference between what would have happened versus what did happen, but they let up fairly early, and you can see the second wave, right? And then Philadelphia was a famous one because there was a parade there and they didn't want to shut it down. So they had the parade, then they shut down, and you can see the difference between the worst case scenario and what happened. There wasn't a lot of difference between those, right? So different kinds of policies in different cities led to different outcomes. And we see that beautifully in this paper in the historical data. Okay. So yeah, so anyway, that's enough about that. So we were looking at the early time data for 2020 and trying to figure out which model to use, but we were going beyond just choosing like parameters for SEIR. We were trying to figure out, do you even use SEIR, because the data is so sparse, it's not very much data. So we compared 3 different classes of compartmental models. Actually, one of them is not a compartmental model. So this one is the Hawkes model. This is a self-exciting point process model that is very similar to like a stochastic SIR, except that there's one process. You don't have you don't have a process for infection and a separate process for recovery. You lump it all into one process here. So this is, and you can also include a dynamic reproductive number. And we do see that in the data. So for example, if you look at China, so if you want to measure like effects of distancing measures, that would be a measurement of your dynamic reproductive number. So if you look at China early on, you can see that the dynamic reproductive number starts out around 3 from the measurements of the data we had, and then decreases kind of, you know, with a little bit of an increase in March, and then decreases quite dramatically. And then you have Italy here, right? And you can see there somewhere, you know, we have error bars, and then we have the, you know, the mean for the calculation, and then the US over here. And then early on, our predictions for what the R-naughts were for California, Indiana, and New York. And you can see that New York and California were quite different in those initial forecasts, which likely led to the vast disparities in the fraction of the population that was infected in the first few months. And by the way, another issue apart from vaccines in terms of preventing death and in terms of why you might want to have tighter controls early on is when you have a novel virus, the medical profession doesn't know what to do with it, right? So I was paying attention to the EM Rap show and talking to some emergency medicine doctors early on, and they were like, you know, do we put people on vents right away? Do we try to give them supplemental oxygen? Do we use, you know, various pharmaceutical interventions that haven't been tested on this disease? They don't know what they're basically going by the seat of the pants early on. Having even a month or 2 of data allows to buy some time to come up with better hospital interventions to try to save lives. So that's another issue that can be affected by you know, more controls early on, just so that your ER docs can try to get their head, and the ICU docs can try to get their heads around how to best treat the really sick patients. Okay, so what we did was we looked at the very early numbers for these 3 states, and we looked at both the confirmed case counts and the deaths. So the confirmed case counts are going to be much more data than the deaths for early time. And we compared using the AIC, these 3 models, SIR, SEIR, and the Hawkes process. And what you see coming out of this, and this was not a surprise to us. So by the way, AIC favors models that have fewer parameters. And so, you know, so the question really is, does the data demand a model with more parameters or not? That's what AIC is asking. And so not a surprise, we're seeing for the mortality data, here's California, it's picking SIR as the most appropriate. Indiana also picking SIR, New York also picking SIR. That is the model with the least number of parameters. And it's also the data for which we had the least amount of data. So we were not surprised to see that outcome for the early time data. At the same time, with the confirmed case counts, you start picking up some of the other models as being perhaps more appropriate, right? And we know that the virus has this delay for exposure. So we start seeing the SIR showing up here for California confirmed cases, same thing with Indiana confirmed cases. And then for New York, we were picking up the Hawks as the better choice. And this is, you know, I mean, this is early time data. You can get a lot of different results. There's noise in the data, but anyway, you have to try, right? So if you want to see what those look like in terms of fitting to actual data points, what you see, and these are the different, there's sort of 6 different studies here. And you can see that SCIR and SIR early on, the exponential, we're looking at the log of the counts versus the dates. So that exponential growth is going to give you a straight line, and you're seeing those straight lines. And then, but you know, the data is a little bit less than straight. And so the Hawks gives you the dynamic reproductive number. So it's going to be piecewise straight lines, right? So you can see that here. And what you're seeing with the Hawks model is kind of what I was alluding to earlier, that you might see higher exponential growth at very, very early times, and then it will kind of plateau a little bit, not plateau, but it will, that rate will decrease a little bit. And you're seeing that in basically all of the Hawks curves here. Okay. So yeah, so that was our study for the early time data. We published that in PNAS. About a little over a year ago. And so more recently, we've been looking at other issues related to both data and models that we think are important. So the first one that I wanted to look at, and I think this is really important for a pandemic in which, you know, not everybody lives in New York City, right? Many people are living in smaller communities, on islands, for which the SIR and SCIR models assume a fully mixed population. So that means that you know, a lot of people can come into contact with a lot of different people at some sort of uniform rate. You know, New York City would make sense for, you know, New York City not under lockdown would make sense for a compartmental model, maybe Los Angeles too. But if you're in a small town, right, where people live on farms, right, and they don't have a lot of interaction face to face, you know, you're going to expect that the dynamics of an outbreak will not follow an SIR model, not necessarily. You're going to expect that the small population size and the lower infection rates are going to lead to very, very different behaviors. And so it would be good to try to model those in a way so that we can estimate things like variances. You know, because if you're trying to come up with policy decisions for your rural populations, you need to, you know, using an SIR model may not be the best choice. So this is work that we have finished, and it's under review with my student Xia Li and former postdoc Chen-Tien Wang and former student Hao Li, looking at a martingale formulation for the stochastic SIR model. And then looking at how that works for some specific COVID examples. So I'll just kind of, I don't have a lot of time, so I'll just kind of give you the rough idea. So, so you take your SIR model, but in the stochastic form, right? So you're looking at individual accounts. In the large N limit, you can prove that stochastic SIR will converge to your standard compartmental ODE model. What do you do with like in between? Like you're not kind of in the large N limit. Well, one way to deal with that is using a martingale formulation. So the martingale part of the model, which is this one here, is going to measure basically the departure from the actual SIR part of the, you know, the mean field part of the model. So and that turns out to be a martingale, and we've got a lot of theory from probability to be able to understand that. So we've tried to put our heads together to use that information. And so one of the things you can do is you can calculate the variances of the martingale part, and you can get some expression for the infinitesimal variances. And what these expressions do is they start to give you like some very naive understanding, at least on how the variances scale with the size of the population. So this is strictly a finite size issue. And we also have some sharp estimates before. So blow up time means that for a stochastic simulation, you can actually have actual instances of the simulation that don't actually lead to a full, you can't continue time forever, right? You have a finite time issue. It's not common, but you always have to put that caveat if you're looking at these stochastic simulations. And you see that the variance is also bounded by a constant over n. And you can use this to prove existence of the continuum limit if you want to do that. But you can also use it to literally estimate variances and to try to use that to understand what the finite size effects are for epidemics. So one of the things we did was we looked at the scaling property as a function of the total population size, and these are realizations versus just the simple 1/n scaling, and you can see it fits quite well. And then we looked at some actual field data, and we looked at parameters from field data. So let's see, so we have Churchill County in Nevada, which had an outbreak about a year ago. And so the actual outbreak is shown here in the dark line. And then what you're seeing superimposed on it are a bunch of realizations of the stochastic SIR model using the same parameters that we got from trying to estimate just from the field data. Notice that over here at early times that there are going to be actually some simulations that never give you like a full outbreak. So that's another thing that happens with these finite size effects, is that you can also have the outbreak will extinguish itself just from a probabilistic point of view. You can also look at the envelope of these solutions versus the actual field data. Here's a cruise ship. So this is a very small, so this county is 26,000 roughly. You want to get to really small populations, but but where outbreaks are important. The Diamond Princess, of course, was in the news, and we had some data from that. It's not like there's obviously going to be some noise in the data, but taking the R0 and the total population of the cruise ship that was estimated, you can see that a bunch of realizations of this outbreak versus the actual data, they kind of fit together, but there's sort of this envelope effect that, you could have had a bunch of different outcomes, right? You certainly don't get one specific SIR curve that the probabilities make a big difference with the small population size. Okay. Yeah, I think I don't have a lot of time, so I have a lot to cover. So I think what I want to do is I want to move on quickly to, and I'm looking at the clock here, I've got like 5 minutes, right? Yeah, okay, so I'll just mention a few words. So we have a paper that that was inspired by some other earlier work on measuring, so we're looking at the dynamics on networks, right? Because the other thing that epidemiologists tell me, and I've talked to a number of them in the last year, is that the basic compartmental models are very well studied from their perspective, but they feel that that the real kind of an area where new research is important is to look at spreading on networks, because in real life, the people's contact networks are not what you would see in an SIR kind of setting. So in my group, we've spent many years looking at something called modularity, which is a measurement of communities in networks. And I will mention that, so I was sort of inspired to do networks, to look at the network problem because of, let me go to this picture. This is an older paper from about 10 years ago, Salathe and Jones, looking at some synthetic networks and looking at the SIR model, where you can control the structure of the network for ones that have high modularity and moderate level of modularity. So you have strong community structure, but probably smaller communities. And what you see when you don't have this really strong community structure is sort of a standard kind of one peak epidemic. But when you have these strong community structures, what you'll see is you'll get little mini outbreaks that kind of go on and on and on and on and on, right? And we have certainly seen field data for COVID-19 that is reminiscent of this kind of behavior, right? So, so I thought that was interesting. And so what we've done, and this is a paper now that's coming, it's on the archive, so you can go read it if you want. It's coming out in M3AS. And it's on so we looked at a multi-layer network model, and we felt this was a very relevant problem for the pandemic today, because we want to look at the coevolution of both the spread of the actual virus and the competing opinions. So this is looking at opinion dynamics coupled to the virus. And these opinion dynamics would be either pro or against like distancing measures, although one could look at vaccines too now, right? Because that's big in the news, right? About the role of vaccines in terms of the spread of the disease. So basically you have a physical layer, which is your compartmental model, but there are three different categories, right? You've got the spread involving people who are pro-physical distancing, anti-physical distancing, or maybe some, sort of neutral category. And then you have the information layer, where you start off you start off without having an opinion. And this is also using an SIR type dynamics. You come into contact with somebody who has an opinion, then you decide you want to share their opinion, and the opinion could either be one of these two compartments, right? So it's a double layer compartmental model where the information spread has a different network structure from the because your physical contacts may not be the people that you're tweeting with on Twitter, right? Or on Facebook or something like that, right? So that's the idea. And then, you can have fun with this. So what we did, and this was largely a group of students that was led by my joint graduate student, Cayenne Peng, who's also supervised by Mason Porter. So what we did was we looked at the stochastic models for these things. And then we looked at trying to get continuum limits by developing, you have to look at the full network structure. And we sort of organized it like a lot of people do by the degrees of the nodes. And then we developed a closure model, right? And so that gets you to a couple set of ODEs, but they're based on these, different degrees, right? So it's a little bit complicated, but nevertheless, you can compare the ODE reduction, because we'll have like maybe 10,000 agents in the full model, but then you have a couple set of ODEs that are much smaller for the closure model, right? And so you can see that overall, we found the closure model worked really, really well compared to the simulations. And then you can start measuring the effects of pro and anti-physical distancing on the spread of the actual epidemic and, how everything couples together. And I don't have a lot of time left, so I think I'm just going to say that, you do see rather marked effects. Also the network structure, looking at things like the role of sortativity in the network structure. And you can see very, very different effects. So bottom line is the network dynamics, both for the spread of information and the spread of the disease, the network structure, can make a huge difference. And the dynamics, as we know, just from reading the news, right? The dynamics about information spread and opinions, right? I'm not saying, I don't want to talk about facts here. I'm going to just say it's opinions, right? Because even if you're making an informed decision based purely on scientifically validated peer-reviewed facts, people can still have different opinions about whether we should be emphasizing prevention of spread versus the economy, right? There's a lot, kids going to school, right? There's a lot of issues here, right? So I'm not going to say anything about that. I just want to say that people have opinions and those will spread. And we see very, very different outcomes as we play with the parameters. So this is all on the archive and you can read that. And I think I'm going to stop because we are out of time. So I'll just say that this is a degree-based pair approximation of the time evolution of the expected number of individuals in different compartments. It's applicable dynamics on heterogeneous networks. And it's mostly a paper that does numerical simulations compared to the closure model, looking at varying different effects. So I think I'm going to stop there. And yeah, so that's it. And I want to thank everyone for coming. This was really nice to be able to talk to everyone today.
Yeah, thanks a lot for the nice talk. So if anyone has questions, you can please feel free to either unmute yourself if you have the ability, or ask questions through the Q&A tool. I was wondering about something that's probably sort of simple and potentially dumb, but we know that with COVID, at least, you can get reinfected even if you've been vaccinated or had it before. What's the easiest way to adapt an SIR model so that you can account for that, or does it not really matter?
Oh yeah, you can, sure. Yeah, sure. There are models out there. Sure. You just have to put them back from the recovered population into the susceptible population. It's a little tricky though, because, the conventional wisdom today, right, is that if you are recovered, you may still get infected, but you may have more immunity, right? So you're, in some sense, you're not quite like the original susceptible compartment, right? So it's not clear. One could introduce, like gradations of susceptibility, right? And that makes it much more complex, right? It's kind of like, going to the kinetic case for PDEs, right? Right. So one could think about doing something like that. And we know also, just to remind everyone, that we have a very heterogeneous population in terms of age and comorbidities, and those are also going to affect things too, right? And age also affects things like immunity, not just the likelihood of dying of the virus. It affects immunity overall. So really good question. I think that there's, excuse me, a lot to do in this area. And my personal opinion is that, okay, this is a little bit morbid, but my personal opinion is that I think that we were damn lucky that the world made it through 100 years without this happening, okay? I also think that COVID-19, we could consider to be something of a dry run, because it's very possible. I mean, there's plenty of diseases out there that are much more likely to cause death than COVID-19, right? And so I hope that the scientific community is learning from this and trying to develop tools. I think we have the potential here to develop some tools that will be helpful to policymakers, to to the medical profession, to public health departments going forward, not necessarily for COVID-19, but for the next thing that comes down the road, right? So that's my opinion.
Yeah, great. There's also a question about if you could just flash a request that you flash the martingale article, the first one about bounding the variance.
Oh yeah, we don't have that one on the web because it's still under review, and we're going to wait to put it online. But sure, I can go back to the slide.
Okay. Yep.
Yeah. This one here is accepted for the network model is accepted for publication. That's on the archive. The martingale model, and the martingale model is actually motivated by some work I've done earlier on some other kinds of sort of self-exciting behavior processes. But yeah, this is the first time we've applied this to COVID, and it's really not that hard. This is not a PDE, it's an ODE. Yeah, so basically, this is how you define your martingale. This is so these are the stochastic SIR, right? And then the GNs are defined literally here, and then the martingale is what you've got left over. I think was that what they wanted to see?
I think so, yeah. And to know when they might expect to be able to see a preprint.
Yeah, they can email me, and right, if somebody wants to see a preprint, send me an email and I'll talk to my collaborators.
And then one last question, I guess, in the chat about where you find all the nice data you were using for your first paper to.
Oh yeah, sure. So good question. If you go to the paper, all the data references are there. PNAS, by the way, is very, very picky. So if you're going to use real data in a paper, they want the data, right? So You can go to the link to the paper and find all that information. But, you know, the short story is we basically went to I believe it was the Johns Hopkins website, right? The one that was plague.com or something early on, right? They were keeping track of quite a lot of data from all over the world. So we were largely using that. But the details are in the manuscript.
Right.
So I have a quick question about the 2-layer model.
Yeah.
Did you get a chance to compare it on the basis of like the AIC to other models, or does it make sense to do so even?
Oh, right. So good question. Good question. So right. So there's a lot of like floating things going on here, right? So we're not trying to look at real data here, right? We're not trying to fit a model. What we're doing, this is a counterfactual study. And it's good question. And it's a counterfactual study with synthetic networks. So we're not actually trying to simulate, you know, San Francisco, right? Right. In fact, that's a beautiful question right there. Is if you wanted to use a network model for, say, San Francisco, what the heck's the network going to look like? Do we even know what the contact network should look like, right? Good question. So if you go and read the original March 16 paper, right, from Imperial, that one's not a network model, but it's kind of like going in that direction. They had some statistics about, they kind of broke the population down into people who were out in the community a lot and people who weren't, right? And then they looked at mixtures within these different kind of subcompartments. Spain also has done that, right? Arenas has a paper early on they were asked to do this by the Spanish government, right? To develop models for Spain, for the different autonomous regions. And they break it down into ages, right? So really, really, really good question. But I think even today, you know, like when we were looking at the early time, one of the things I was very concerned about was outbreaks in nursing homes. Why? Because my little sister works in a nursing home, right? And guess what? She got COVID early on, right? Mild case, she survived, she was fine. She saw 20% of her patients die in a month, right? In New Jersey. It was just sad. It was a disaster, right? And so, you know, nursing homes are a very good small case study of how do we model networks, because you've got people who live there full time, the patients, and you've got people who come in, rotators who come in to help take care of the patients, people who give them treatment, doctors, just the regular staff that are the nursing care. And so there are people who are going from one nursing home to another doing things. And then you've got the staff who go out into the general population. By the way, the same thing, I had a discussion with the NBA early on about the bubble, right? And whether they were going to, you know, just use Orlando for the NBA finals. I don't know if you guys remember the NBA bubble, right? And so that was another question, is like, you know, we were having just very much, you know, kind of like discussions about, well, you know, where is your outbreak going to come from, right? And they were like Las Vegas, you know, and yeah, and so you kind of just walk them through what the contacts look like. And, you know, you have players in Vegas and you tell them they have to stay in their hotel room all the time and they can't go out. That's kind of tough, right? Orlando might be easier to do that, right? And so, you know, and my understanding was from the bubble that the infections were largely coming in from the working staff, right? They were testing everyone and they were catching people who are, you know, who are out in the general community, but the players were not allowed to go out into the general community while that was happening, right? So, you know, there's a lot of like sub cases like this where having really good network models could be very helpful, especially for future kind of, you know, decisions like this. Also, I mean, there's a lot of different subpopulations for whom this could be beneficial, you know, right? School populations, kids in school, college campuses. We had some students, we have a lot of other work that's not like papers that I'm ready to show you, but I can just say that we did have some students do class projects in a graduate course that I co-taught with Marcus Rober. And they were looking at some of the data from the UCLA campus, looking at how many students are enrolled in different classes and how big the class sizes are, right? And looking at network models based on that, and also network models based on some publicly available data sets for students coming into contact with each other that's available on the internet. So we've had a lot of fun looking at these, but I think this is a wide open problem, really, to be honest. And if you're going to try to stop a future pandemic early on, understanding these kinds of dynamics on these smaller scales is absolutely critical, right? Because once it's out in the general population, you're done, right? So good question.
Thanks.
Thank you.